Hi, good morning. Today we are going to discuss one theorem and theorem 6.3.2. This is about the convergence of monotone and bounded sequence of operators. This is about convergence of monotone and bounded sequence of operators. Okay. This is like our this is theorem monotone in real analysis monotonic increasing secant which is bounded above is convergent like that. Okay, so here we are considering, listen carefully, a sequence of operators a naught, a1, a2, etc. And this is actually a naught less than or equal to a1 less than or equal to a2 less than etc. less than or equal to an less than or equal to etc. less than or equal to a. Clear? This is a monotonic, actually increasing sequence. Okay, and this is less than or equal to a. This is bounded by a. Then the theorem says that there exists a strong limit of an. There exists a strong limit of a. The theorem says that there exists a strong limit of a. Okay, sequence a. This is sequence a and n. Now, what is the meaning of strong limit? That is, there exists a bounded operator b and a and x converges to bx for all x belongs to h. That is, we have to prove that there exists a bounded operator b and our a and x converges to bx for all x belongs to h. Then we call this as a strong limit. And an has a strong limit. Our sequence is a and n. Okay. Now we are moving to the proof. So, hope the statement is clear. We have to find a sequence, we have to find a bounded operator B such that our ANX converges to BX. Okay. For this, actually, we are proving, first we are proving ANX. Our ANX, this sequence ANX is a Cauchy sequence. Okay, that is our first aim. Now for this, we are stating one result. For every symmetric operator A, there is a number C such that A less than or equal to C into I. For every symmetric operator A, there is a number C such that A less than or equal to C. Actually, as per this, C greater than 0. So we can, how we get this result? We have one result. There is no need to write this in your note. We have one result. That is minus I less than or equal to A less than or equal to I implies norm of A less than or equal to 1 and use property 6.115. We get minus I A less than or equal to A less than or equal to I into norm of A. Norm, if A is a symmetric operator and then norm A equal to, you know that norm A equal to supremum of x not equal to 0 modulus of inner product A x by okay. So that means clearly there exists, or you can say norm of A is a particular value. Okay. So we are denoting that as, or you can take C as some value greater than norm A. Okay, that means C, that there exists a C such that A less than or equal to C into I. As norm always positive, we can easily say that C is also positive. Okay. So for a symmetric operator A, there is a number C such that A less than or equal to Ci. Now, as A and A naught are symmetric, clearly A minus A naught is symmetric. That already we have discussed in our last class. So, A minus A naught is symmetric. A is symmetric means there exists a C. Okay. As A minus A naught is symmetric, there exists a C1 such that A minus A naught less than or equal to C1 into I. Okay. This implies A minus A naught divided by C1. We are choosing C1 as positive. Therefore, A minus A naught divided by C1 is less than or equal to I. So we have given this sequence, and from this we can write like this: 0 less than or equal to A1 minus A naught less than or equal to A2 minus A naught less than or equal to etc. Okay, less than or equal to A minus A naught less than or equal to C1I, and like this. So from this result, we can say that without loss of generality, we can assume that 0 less than or equal to an less than or equal to I. Without loss of generality, we can assume that 0 less than or equal to an less than or equal to I. Suppose this is not true. That means you can replace an by some an minus a naught by c1. That means this an is, what is our an? An is uh, sorry, if this is not true, then we can say that you can take this as some, replace this by a1 e2 etc an, then we get a sequence an such as 0 less than or equal to an less than or equal to 1. Okay, instead of an, if this is not whole, instead of an we can assume an minus a naught by c1. Okay, that means 0 less than or equal to an minus a naught by c1 less than or equal to I. Okay, so whenever this is not whole, you can assume this as this part as a. Okay, or you can use another notation like some dn equal to. So we get 0 less than or equal to dn less than or equal to I. And for all other work, you can replace an as dn. Okay, no problem. Hope everything is clear. So no need to write all these things. Okay. Without loss of generality, we can assume that 0 less than or equal to an less than or equal to I. Now, for n greater than or equal to m, we define amn is equal to an minus am. For n greater than m, we define amn equal to an minus am. N greater than m, that means an is greater than or equal to am. An is greater than or equal to am means an minus am is greater than or equal to 0. Clear? We have an am less than or equal to an, because n greater than m. A's are increasing sequence. So am less than or equal to an. So a less than or equal to b means b minus a greater than or equal to 0. That is an minus am is greater than or equal to 0. So we have this one. We have 0 less than or equal to an minus am, which is less than or equal to an, and this is less than or equal to I. Because why? An, we have an greater than or equal to 0. We have am is, we have am greater than or equal to 0. And am you can write as an minus am. Okay, and this is greater than or equal to 0. We have am greater than or equal to 0 because we have 0 less than or equal to an less than or equal to I. If you take any n, we have this result. So am is also greater than or equal to 0. Okay. So an minus am is greater than or equal to 0. That means an minus am is less than or equal to an. So we have 0 less than or equal to an minus am is less than or equal to an is less than or equal to I. That means 0 less than or equal to amn less than or equal to I. Yeah, clearly minus I less than or equal to amn less than or equal to I. So using the first property, norm of amn less than or equal to 1. And we have generalized Cauchy-Schwarz inequality, this one. So for any x and y equal to am and x, we have norm of amx minus anx whole square. What is this one? Am minus anx. Am minus amx whole square. Norm of am minus anx whole square. And this is amnx whole square. Now norm of amnx whole square is equal to inner product amnx. And we are taking y equal to amnx. Therefore, this is actually amnx y. And if you take modulus, this inner product is less than or equal to its modulus. And this is less than or equal to by Cauchy-Schwarz inequality amnx x, amn y, amnx x, inner product amnx. Y you can replace by amnx. So root of amnx x, root of inner product amn square x, amnx, root of inner product amnx x, and this amnx, here we are again applying this result, Cauchy-Schwarz in terms of norm. That is, we have this result, inner product of xy modulus of this is less than or equal to xx all raised to 1 by 2 yy all raised to 1 by 2. Okay, and this is same as norm of x. So this term is replaced by norm of amn square x, and this term is replaced by norm of amn x. Okay, root of. So there is, here we have, this is less than, sorry, here we have this is less than or equal to, this is actually norm of x, sorry, norm of x, and this is norm of y. So here norm of amn square x and norm of amn x. Okay. Now what is norm of amn x? This is less than or equal to norm of amn into norm of x. But norm of amn less than or equal to 1. Therefore, norm of amn x less than or equal to norm of x. Now what is norm of amn square x? This is less than or equal to norm of amn into norm of amn x, and this is less than or equal to 1 into norm of amn x into norm of x, and this norm of amn is less than or equal to this is, therefore each of these term is less than or equal to 1. Less than or equal to norm of x. Therefore, this is less than or equal to norm of x into norm of x square root norm of x. So, thus we get root of amn x x norm of x. That is, we get norm of amn x minus anx whole square is less than or equal to this one. But this value is actually am minus anx. Okay. So, and this is root of am minus an x x into norm of x, and this is root of inner product amx, sorry, amx x minus inner product anx x norm of x. Now anx is a monotonic increasing bounded sequence, therefore it is converges. We choose am greater than or equal to an. That means inner product of this one greater than or equal to 0. That means anx x is greater than or equal to amx x inner product. Also I greater than or equal to an. That is ixx greater than, okay. And this is a bounded value. So amx x is an increasing sequence of, this is actually bounded or complex numbers. Okay, inner product bounded sequence. So monotonic increasing and bounded sequence, therefore it converges. Therefore sequence AMNX ANX is a Cauchy sequence, converging sequence, Cauchy sequence. Therefore this difference, this is actually tends to 0 as m comma n tends to 0. Thus we get norm of amnx minus nx whole square tends to 0 as n tends to infinity n greater than m. Okay, therefore norm of amx minus anx whole square tends to 0 as n greater than m tends to infinity for all x belongs to h. That means this is a amx is a Cauchy sequence. Anx is a Cauchy sequence. So this sequence is a Cauchy sequence. That means limit anx exists. Now we define b from h to h as bx equal to limit anx. This limit exists. The result says that limit anx exists, and we are denoting this limit as bx. Okay. Clearly x belongs to h and anx belongs to the range. So and we are so that means the limit also exists in this ranges. So we are denoting bx as limit anx. Okay. Now what about bx plus y, limit an x plus y, limit an x plus any, limit an x plus limit any, and that's equal to bx plus by. Now bcx. Okay. So b is also a linear operator. And we have 0 less than or equal to an less than or equal to I. That implies 0 less than or equal to inner product anx x less than or equal to ix x. That is 0 less than or equal to anx less than or equal to ixx is norm of x square. 0 less than or equal to inner product anx x less than or equal to norm of x square. Taking limit throughout, we get 0 less than or equal to limit here. Bxx less than or equal to norm of x. This implies each this is less than or equal to norm of x. That means B is a bounded operator. Thus we get ANX, the sequence ANX is a, thus we get this BX is a bounded operator. That means ANX is a sequence and that converges to a bounded operator B. That is we get sequence A. Okay. It's a bounded it converges to a bounded operator B. That is what we have to prove. Just to look at back to the statement. A naught, A1, etc. Then there exists a strong limit of A n n. That means there exists a bounded operator B and ANX converges to BX for all x belongs to H. Thus we have proved ANX converges to BX for all x belongs to H. Next is again a one result that we will discuss in our next class. Okay.